a signal has arrived from deep space that should not exist at all. It is not a burst. It is not noise. It is not something scientists can place into any known category. It repeats with a structure that looks intentional, yet there is no known object in the universe capable of producing it. Every time it appears, it carries a level of energy that should not survive the journey across billions of light years. And yet it keeps returning. For the first few seconds after the detection, scientists believed it was a mistake, a glitch in the system, a random spike in data. This happens more often than people think in astronomy. Space is full of interference, cosmic noise, and instrument errors. But this signal did not disappear. It returned again and again, each time with the same strange pattern, as if something deep in space was trying to repeat a message without breaking its structure. Modern telescopes are designed to detect the faintest whispers of the universe. They scan the sky using radio waves, capturing signals that travel across billions of years. These instruments have revealed pulsars, quasars, black holes, and even the faint afterglow of the Big Bang itself. But they also reveal something more unsettling. Not every signal fits into known science. Some arrive without explanation. Some behave in ways that challenge the rules of physics. One of the most mysterious classes of signals ever discovered is known as fast radio bursts. These are extremely short and powerful pulses of energy from deep space. For years, they were thought to be rare and random. A one-time cosmic event, a star collapsing, a magnetar flaring, a violent explosion somewhere in the distant universe. But as telescopes became more advanced, scientists began to notice something unexpected. Some of these bursts repeat. Some follow patterns. And some behave in ways that do not match any known cosmic event. Even then, researchers believed they could eventually explain them. That confidence is now being tested, because this new signal is different. It does not behave like a typical fast radio burst. It does not fade into randomness. It does not come from a single explosive moment. Instead, it appears structured, controlled, almost rhythmic. That alone breaks expectations. In nature, extreme cosmic events tend to be chaotic. They do not repeat with precision. Yet this signal does exactly that. Astronomers first detected it using radio telescopes designed to scan large sections of the sky. These instruments do not see light. They see radio waves, the same type of energy used in communication systems on Earth, but stretched across cosmic distances. When a signal appears, it is recorded as a pattern of energy over time. Most signals are easily identified. They match known sources like pulsars, which are spinning neutron stars that emit beams of radiation like cosmic lighthouses. Or they match background noise from galaxies, stars, or even human technology interference. But this signal matched nothing. It came from a region of space so distant that the light itself has been traveling for billions of years. That means whatever created it existed in the ancient universe, possibly before Earth even formed. Yet the signal arrived clean, structured, and unusually strong for its distance. This is where the mystery deepens. According to known physics, energy spreads and weakens over distance. The farther it travels, the weaker it becomes. But this signal does not behave as expected. It arrives with a consistency that defies normal decay. At first, scientists attempted to dismiss it. Instrument error was the most comfortable explanation, but multiple observatories detected the same pattern independently. That removed the possibility of a single malfunction. Then came the second detection, and the third. Each one confirmed the same structure, the same rhythm, the same impossible consistency. This is where the scientific community became concerned, because the universe is supposed to follow predictable laws. Even its most violent events, like black holes or supernova, operate within the boundaries of physics as we understand them. But this signal sits outside those boundaries. It does not break one rule. It breaks several at once. And that raises a deeper question. If this signal is not random noise and it is not a known astrophysical event, then what is it? In this video, we will explore the full story behind this mysterious deep space signal. We will break down how it was discovered, why it confused scientists from the very first moment, and why it is forcing researchers to question what they thought they knew about the universe. You will see the leading scientific explanations, the competing theories, and the uncomfortable possibilities that some experts are only beginning to discuss. Some of these explanations stay within known physics. Others go far beyond it. And by the end, you will understand why this single detection has become one of the most debated mysteries in modern astronomy, and why it may represent more than just a strange signal. It may represent a gap in our understanding of reality itself. If you are interested in space, deep science, and the unknown edges of the universe, make sure to stay until the end. What you are about to hear challenges some of the most basic assumptions about how the cosmos works. And if you are new here, welcome to the channel. Subscribe now, because we explore the biggest mysteries in science, space, and the universe, where every answer leads to a deeper question. The first detection came through a radio telescope array scanning a quiet section of the sky. At first, the data looked normal, just background noise from deep space, random fluctuations, the kind of signals scientists see every day. But hidden inside that noise was something different, a pattern that should not have been there. It was not a single burst. It was structured, clean, repeating in a way that immediately stood out from everything else in the data set. Most cosmic signals arrive as chaotic spikes. They rise and fall without order. This one did not behave that way. It followed a pattern that appeared too precise to be natural. When researchers isolated the signal, they noticed something even more unusual. The timing between each pulse was consistent, not perfectly mathematical, but stable enough to suggest repetition. In the universe, repetition with structure is rare. Natural processes tend to drift. They change over time. Stars rotate, black holes fluctuate, plasma clouds scatter. Yet the signal stayed steady. Fast radio bursts, or FRBs, are known for their extreme power and extremely short duration. They last only milliseconds. Most are one-time events, a single flash from deep space and then nothing. This signal did not behave like that. It did not vanish. It returned in multiple detections with the same internal rhythm. Even more unusual was its intensity. Normally, signals weaken as they travel across billions of light years. Space stretches them. Energy spreads out. But this signal maintained a surprisingly stable strength across each detection. It did not show the expected fading pattern. That detail alone raised concern among the researchers analyzing it. The signal also failed to match any known cosmic source. Pulsars, for example, produce highly regular pulses, but they spin with exact rotational signatures that can be measured and predicted. This signal did not align with those patterns. Quasars, which are powered by supermassive black holes, emit broad and noisy radio waves, not clean repeating structures. Magnetars can produce bursts, but those bursts are violent and unpredictable. None of these explanations fit. Scientists ran comparisons against every known catalog of astronomical objects. The result remained the same: no match, not even a partial one. Then came the most unsettling detail. The origin point of the signal appears to be extremely distant. Estimates place it at billions of light years away in a region of space where the universe was still forming complex structures. That means the signal began its journey long before Earth existed, before the solar system formed, before even the Milky Way reached its current shape. Despite that distance, the signal arrived with a level of clarity that should not be possible. Intergalactic space is filled with interference, gas clouds, magnetic fields, cosmic radiation. All of it distorts signals over time. Yet this one passed through all of it without losing its structure. As more data came in, scientists realized they were not dealing with a typical astronomical event. The signal was not only unusual, It was consistent across multiple observations, and each new detection added another layer to the mystery, making it harder to explain using any known astrophysical model. When scientists began to analyze the signal in detail, the first concern was its energy stability. In deep space, extreme energy events are expected to behave in chaotic ways. A supernova, for example, releases an enormous amount of energy in a violent explosion. But that energy is uneven. It spreads irregularly. It fades with complexity. No two measurements look exactly the same. This signal did the opposite. Each detection showed nearly identical energy levels. Not perfectly identical, but stable in a way that immediately stood out. That consistency should not exist in a natural cosmic event of this scale. Even the most powerful astrophysical sources fluctuate. Stars pulse, black holes shift, plasma jets twist and scatter. Nothing in the universe behaves like a perfectly repeating system over vast distances. The repetition pattern added another layer of confusion. In known astrophysical processes, repetition comes with variation. Pulsars rotate with extreme regularity, but their signals are tied to physical spin rates that slowly change over time. They also carry clear signatures of their magnetic fields and rotational geometry. This signal did not match those signatures. It repeated, but not in a way that fit any known rotational or orbital system. Researchers noticed something even more unusual. The timing between pulses showed an internal structure that suggested precision, not perfect mathematical symmetry, but a controlled rhythm that resisted natural decay patterns. In physics, randomness is expected at cosmic scales. Even-ordered systems slowly drift due to gravitational influence, radiation pressure, and quantum-level fluctuations. Yet this signal held its timing across multiple detections with minimal variation. That level of stability led to uncomfortable questions. One possibility raised early in the analysis was whether the signal could be artificial in origin, not necessarily from a civilization, but from a process that behaves like engineered structure. The reason for this thought was simple. In nature, precision is rare without feedback systems. Machines, by contrast, produce repetition through design, but even this idea faced problems. No known technology could survive the journey from billions of light years away while preserving such structure. Every natural explanation was tested. Magnetars were considered. These are highly magnetized neutron stars capable of producing powerful bursts of radiation. But their emissions are irregular and violent. They do not maintain steady repetition patterns. Quasars were also examined. These are powered by supermassive black holes consuming matter at extreme rates. Their signals are broad, noisy, and inconsistent. They also vary over time, which does not match the stability of this signal. Even more exotic models were explored. Some researchers considered rare plasma interactions in intergalactic space. Others looked at gravitational lensing effects that might distort signals into repeating patterns. But each attempt failed to fully reproduce what was being observed. The combination of stable, energy-structured repetition and long-distance clarity did not fit into any known astrophysical framework. One of the most difficult problems is that the signal does not break just one rule. It breaks several at once. It challenges energy distribution models, signal decay expectations, and timing stability theories altogether. In physics, when multiple independent rules fail at the same time, it usually means one of two things. Either something fundamental is missing from current understanding, or the phenomenon does not belong to any known category at all. As more data was collected, the confidence in simple explanations began to fade. The signal was not becoming easier to classify. It was becoming more difficult to place into any known system of cosmic behavior. The deeper scientists looked into the signal, the more disturbing the results became. The first issue was its energy behavior. In the universe, extreme energy events are expected to be unstable. A supernova, for example, is one of the most violent explosions known in physics. It destroys a star in seconds. The energy released is massive but never uniform. It spikes, collapses, scatters, and fades in unpredictable ways. This signal did not follow that rule. Each detection showed nearly identical energy levels. Not perfectly identical, but close enough to raise immediate concern. That kind of consistency is extremely rare in cosmic events. Even neutron stars, which are among the most stable objects in space, show tiny variations in their emissions due to magnetic shifts and rotational drift. This signal did not display those natural irregularities in any meaningful way. Then came the repetition pattern. At first, repetition might sound normal in space. Pulsars are famous for their repeating signals. They rotate like cosmic lighthouses, sending beams of radiation at fixed intervals. But pulsars are predictable because their rotation is tied to measurable physical spin. They slow down over time. They show timing drift. They carry clear signatures of their structure. This signal did something different. It repeated, but not like a spinning star. The pattern did not match any known rotational system or orbital cycle. It did not show the gradual decay expected from natural cosmic clocks. Instead, it held a structure that seemed too stable across multiple detections. The spacing between pulses did not drift in a way that could be explained by known physics. That led to the third and most uncomfortable observation: timing precision. In physics, precision over long distances is difficult to maintain. Signals traveling through billions of light years pass through magnetic fields, plasma clouds, and gravitational distortions. These factors stretch, bend, and distort the original pattern. Over time, even structured signals lose clarity, yet this one arrived with a level of timing consistency that should have been destroyed long before reaching Earth. Some researchers began to question whether the signal could be highly ordered in origin, not necessarily artificial, but structured in a way that mimics engineered behavior. In natural systems, high precision usually requires feedback loops or stable environments. Neither of those conditions exist in deep intergalactic space at this scale. Every known celestial object was tested against the data. Magnetars were eliminated because their bursts are violent and unpredictable. Black holes were ruled out due to their noisy and broad emission patterns. Even rare theoretical objects like exotic quark stars failed to match the combination of stability and repetition. The problem grew more serious as more observatories confirmed the same structure. Independent detections removed the possibility of local interference. That meant the source was real, consistent, and extremely distant. Yet no known model of space physics could fully explain how such a signal could maintain structure, energy consistency, and timing precision all at once. Each explanation attempted so far solved one part of the mystery but broke another. As the data continued to build, scientists began to split into different camps of interpretation. With no clear answer, the only option left was to explore every possible explanation, even the ones that pushed the limits of current understanding. One of the first ideas was that the signal might come from an unknown type of neutron star. Neutron stars are already extreme objects. They are formed when massive stars collapse under gravity. A single teaspoon of neutron star material would weigh billions of tons on Earth. Some neutron stars become magnetars, which have magnetic fields trillions of times stronger than anything humans can produce. These objects can release sudden bursts of energy, but even they do not behave with this level of stability. Still, some researchers suggested there could be a variant of neutron star not yet observed, a version with unusual magnetic alignment or internal structure that creates more controlled emissions. This idea remains possible, but there is no direct evidence for such a class of object. Another theory moves even deeper into unknown territory. Some physicists propose that the signal could be linked to dark matter interactions. Dark matter makes up most of the mass in the universe, yet it does not interact with light in any known way. It is invisible, detectable only through gravity. In rare theoretical models, dark matter particles could interact under extreme conditions and produce weak electromagnetic signatures. These signatures might appear structured if influenced by large-scale cosmic fields. However, this remains highly speculative. No experiment has ever confirmed such behavior. A third explanation focuses on a more subtle effect in space: gravitational lensing. This happens when massive objects like galaxies bend light and radio waves as they pass through their gravitational field. In some cases, this can distort or duplicate signals from distant sources. Some researchers suggested that the repetition pattern might not come from the source itself, but from the signal being warped along its journey. Still, detailed simulations have failed to reproduce the exact structure seen in the data. There is also a broader category of explanation that some scientists are now considering more seriously: a natural phenomenon that has not yet been classified. History shows that this is not uncommon in astronomy. Pulsars, for example, were once called little green men because their regular signals seemed artificial before their true nature was discovered. Fast radio bursts were also unknown for decades before technology improved enough to detect them properly. It is possible that this signal belongs to a similar category of undiscovered cosmic behavior. But there is one idea that remains the most controversial. A small number of researchers have cautiously discussed the possibility of non-natural origins, not as a claim, but as theoretical consideration. The signal shows structure, repetition, and stability that resemble engineered systems. In known physics, such precision usually comes from controlled processes. That does not mean intelligence, but it does raise questions about unknown mechanisms that could produce ordered emissions across cosmic distances. This idea is not widely accepted. Most scientists avoid it due to lack of evidence and the risk of misinterpretation, yet it continues to appear in private discussions, especially as no conventional model fully explains all aspects of the signal. Each theory explains part of the data, but none of them fully account for everything observed. Scientists compared this signal with every major fast radio burst ever recorded. Over the past decade, hundreds of FRBs have been detected across the sky. At first, they all seemed mysterious. Short, powerful flashes from deep space. But as detection improved, patterns began to emerge. Many were traced back to magnetars. Others were linked to known astrophysical events. Some even showed repeating behavior, but still within explainable physical limits. This signal did not follow that path. Most fast radio bursts last only milliseconds. They appear suddenly and disappear just as fast. This one behaves differently. It persists longer in detection windows, not in a way that makes it continuous, but in a way that suggests structured emission over time. That alone sets it apart from nearly every known burst event. Another key difference is predictability. Natural cosmic bursts tend to vary. Even repeating sources show irregular gaps between emissions. This signal shows a level of timing stability that stands out immediately in the data. The intervals are not perfectly uniform, but they remain unusually consistent across multiple observation sessions. That consistency becomes more striking when compared with the chaotic nature of known astrophysical bursts. Researchers also notice something more. Unusual during signal analysis, it does not appear random. Many cosmic signals carry noise-like characteristics. They look chaotic when broken down into frequency patterns. This signal shows structure, not in a simple repeating wave, but in layered patterns that suggest internal organization. Some scientists described it as resembling encoded information. Not a message in a literal sense, but a signal with complexity that goes beyond random emission. One of the most important findings came from independent observatories. Multiple radio telescopes located in different parts of the world detected similar patterns at different times. This ruled out local interference. It also ruled out instrument error. If the signal had been caused by equipment malfunction, it would not appear consistently across separate systems with different hardware and environmental conditions. This independent confirmation made the signal far more significant. Even more unusual is the fact that known sources of radio noise cannot reproduce its signature. Earth-based interference, such as satellites or communication systems, has predictable patterns that are well cataloged. Cosmic background noise is also well understood and statistically modeled. When researchers compared these known sources with the new signal, the differences were immediate and clear. The structure did not match any known interference profile. Another lesser-known detail is how the signal behaves in frequency space. Instead of spreading energy evenly across frequencies, it concentrates in narrow bands with unusual spacing. This is not typical for natural cosmic emissions, which tend to produce broader and smoother frequency distributions. That narrow structuring adds another layer of complexity to the data. As more data sets were reviewed, scientists realized that this was not just another fast radio burst with unusual features. It was something that consistently refused to fit into existing categories. Each comparison with known signals only made the differences more obvious, not less. The discovery of this signal has created a clear division inside the scientific community. Astrophysicists who normally agree on most cosmic phenomena are now split into two main positions. One group believes the signal can still be explained through natural astrophysical processes. The other group argues that existing physics may not be enough to fully describe what is being observed. The first group focuses on caution. They argue that space is extremely complex and still not fully understood. Many signals that once seemed mysterious were later explained with better data. Pulsars, quasars, and even fast radio bursts all went through this process. According to this view, the signal may come from a rare combination of known objects or conditions that have not yet been fully modeled. They emphasize that the universe is large enough to produce rare events that look artificial or impossible at first glance. The second group, less confident in traditional explanations, they point to the combination of stability, repetition, and energy consistency as something that stretches current models too far. They argue that while individual features might be explainable, the full combination is not. For them, the signal represents a possible gap in astrophysics, where known laws may not be sufficient to describe all observed behavior. A major challenge in this debate is data verification. The signal comes from an extremely distant region of space. That distance weakens its strength and limits the level of detail that can be captured. Even the most advanced radio telescopes are working with incomplete information. Small distortions caused by interstellar gas, magnetic fields, and cosmic expansion make it difficult to reconstruct the original source behavior with perfect accuracy. There is also the issue of signal weakness. At such vast distances, even powerful emissions arrive at Earth as faint traces. That means researchers must work with limited data points. In some cases, only short detection windows are available before the signal fades back into background noise. This makes it harder to confirm whether the observed patterns are fully accurate or partially distorted versions of the original emission. Another concern raised by some scientists is misinterpretation. Space is filled with complex overlapping signals. When multiple weak sources combine, they can create patterns that appear structured but are actually the result of random alignment. This phenomenon is known in radio astronomy, and it has caused misidentifications in the past. Because of this, some researchers argue that extreme caution is necessary before drawing conclusions. At the same time, there is growing pressure to improve observational tools. Current radio telescopes, while powerful, may not have enough resolution to fully analyze this kind of signal. Plans for next-generation observatories are already being discussed. These would include larger arrays, improved sensitivity, and faster data processing systems capable of capturing finer details in real time. There is also a quiet but important shift happening in the background of this debate. More researchers are beginning to accept that current astrophysical models may be incomplete. Not wrong, but incomplete. The universe continues to produce signals and phenomena that stretch the limits of existing theory. This particular signal has become one of the strongest examples fueling that discussion. The universe has once again shown that it is far from fully understood. A signal has been detected from deep space that does not fit into any known category. It repeats. It stays stable. It carries structure that should not exist according to current models of physics. And yet it is real, recorded, and confirmed by multiple observatories. Each new detection like this forces science to expand its boundaries. Not because the laws of physics are broken, but because they may not be complete. Every generation of astronomers has faced moments like this, signals and objects that seemed impossible at first until better tools revealed a deeper layer of reality. This signal now sits in that same uncertain space between mystery and understanding. It may turn out to be a rare natural phenomenon, something occurring under extreme conditions that have not yet been fully studied. The universe is large enough to hide many unusual processes, or it may represent something entirely new, something that does not yet have a name in modern astrophysics. Both possibilities remain open. What stands out most is not just the signal itself, but the reaction it has created. Scientists are cautious, but curiosity is growing stronger than certainty. That is often how major discoveries begin. Not with answers, but with questions that refuse to disappear. There is also a deeper shift happening in the background. Each unexplained signal pushes researchers to rethink assumptions about space, energy, and information across the universe. The idea that everything is already known becomes harder to maintain with each new anomaly. This signal adds to a growing list of cosmic events that challenge simple explanations. In the end, the most important part of this discovery may not be the signal itself. It may be what it forces science to reconsider about the universe, the limits of current models, the behavior of extreme cosmic environments, and possibly the way information travels across unimaginable distances. Somewhere out there, across billions of light years, something is producing a pattern that we do not yet understand. Whether it is a rare natural process or something entirely new, it is already changing how we look at the cosmos. If you enjoyed this deep dive into one of the most mysterious signals ever detected, like this video and subscribe for more explorations into the unknown edges of science and space.